Hello everyone, today I will present about a topic related to the subject communication network and transmission line and consists of the topic 1. Network theorem 2. Series and parallel resonance, multiple resonance 3. Two-part network 4. Filter. And this topic we will talk about network theorem, and this topic consists of the topic 1. Superposition theorem 2. Reciprocity theorem 3. Thevenin theorem 4. Norton theorem. And next we will talk about superposition theorem. Any linear circuit with a power supply has two or more current or voltage source. When the value of the current generated by the power source of each independent power supply to the circuit is combined algebraically, you get the current flowing in each of the different branches of the real circuit. Next, we will do example. Step 1. Determine the direction of the current flowing in this circuit. And step 2. Select the first power supply direction of the current flowing in the circuit. Then calculate the current flowing to each resistor in the circuit. And then we will get this equation from step 2. Step 3. Select the first power supply and the direction of current flowing in the circuit. Then calculate the current flowing to each resistor in the circuit, and then we will get this equation in step 3. And last step, step 4. Then the value of the current are combined algebraically. Then we will obtain the value of the current flowing in the circuit, and we will get I1, I2, and I3. And note if the voltage source is short circuit and if the current source is open circuit. And next we will talk about reciprocity theorem. In a linear bidirectional single source network, the ratio of response to excitation remains the same even when the positions of the response excitation are interchanged. And next we will do example and find the value of current I when the network satisfies this reciprocity condition. And this is example, and we will get this solution, and we will find I is equal 6 ampere. And next, Thevenin theorem. In any linear network, a new circuit can be collapsed into a circuit with a voltage source connected in series with a resistance value. And this example, the method for finding the RTH value can be obtained by step 1. Remove this resistance you want to find current to, and step 2. Remove the power supply, and step 3. Find the resistance at the point where resistance is removed to find the current to it. And you can see that resistance of 10 connect in parallel, in which can be found 5. Follow RTH is equal 10, it may by 2 equal 5. And this example, the method for finding the VTH value can be obtained by step 1. From the circuit, find current flowing in the circuit by Kirchhoff voltage law. We will get this equation, and this equal 1.5. And step 2, we will get this equation. And last step, step 3, we will be able to find the current flowing to RL is the total current flowing in the circuit, and we will get from this equation. And next, Norton theorem. In any linear network, a new circuit can be collapsed into an electrical circuit with a single current source connected in parallel with a resistance. And this example, the IN value can be found by step 1. Take the resistance value that you want to find current flowing to it and short circuit the point where the resistance is removed. And step 2, we will find I1 in at loop 1, and we will get the equation, and we will find I2 at the loop 2, and we will get this equation. And note the method for finding the value of IN has method similar to that of RTH. Okay, in this topic we will talk about resonance, and this topic consists of topic 1. series RLC resonance circuit, 2 parallel RLC resonance circuit, and 3 multiple resonance. And this series RLC resonance circuit resonance occurs in a series circuit when the supply frequency causes the voltage across L and C to be equal and opposite in phase. And then the relationship between resonance bandwidth selectivity and quality factor for the series resonance circuit being defined as 1. Resonance frequency, and we will get this equation, and 2. Current, and we will get this equation, and 3. Lower cutoff frequency, and we will get this equation, and 4. Upper cutoff frequency, and we will get the equation, and 5. Bandwidth, we will get this equation, and last equation, quality factor, and we will get this equation. And parallel RLC resonance circuit. Parallel resonance occurs when the supply frequency creates zero phase difference between the supply voltage and current, producing a resistive circuit. And this we will get the relationship between resonance bandwidth selectivity and quality factor for parallel resonance circuit being defined as 1. Resonance frequency, we will get this equation, and 2. Current in parallel resonance circuit, we will get this equation, and 3. Quality factor, and we will get this equation, and 4. Bandwidth, we will get this equation. And this multiple resonance is desirable when a device operates in various frequency bands. And we will consider the circuit in the figure. The impedance of circuit is given by this, and the frequency at which reactance is zero is called zero frequency, by the frequency at which the reactance is infinity is called pole frequency, and we will get this equation. And FR1 we will call zero frequency, and FR2 we will call pole frequency, and therefore the impedance can be rewritten as this equation. Okay, and next topic we will talk about two-port network, and this topic consists of topics 1. C parameters, 2. Y parameters, hybrid parameter or H parameter, and last topic transmission parameter. And two-port network, measuring the signal between input and output size by arranging the network circuit to be measured with only the input and output. We can write network elements with parameters representing network characteristics, leaving only 4 parameters. And C parameter, we will get this formula from this picture. And this formula in this picture, we will get V1 is equal C11 I1 plus C12 I2, and V2 is equal C21 I1 plus C22 I2. And this C parameter example, write the equivalent circuit in the form of C parameter. And step 1, we will find C11 and C21 by opening the circuit at port 2. When we determine I2 is equal to 0, and we get this equation. B1 is equal R1 plus R2 multiply I1, and B2 is equal R2 I1, and we will get this equation. And step 2, find C12 and C22 by opening the circuit at port 1, and we will determine I1 is equal to 0, and we will get V1 is equal R2 multiply I2, and V2 is equal R2 multiply I2, and we will get this example, and we will get to write a metric form in this picture, and we can write equivalent circuit. And next we will talk about Y parameters, and we will get equation from this figure, and this picture is equation is I1 equal Y11 V1 plus Y12 V2, I2 is equal Y21 V1 plus y22v2. And this y parameter example, write the equivalent circuit in the form of y parameter. Step 1, find y11 and y21 by short the circuit at port 2 when we determine v2 is equal to 0, and we will get I1 is v1. I1 is equal v1 divided by R1, and I2 is equal minus I1, and we will get this formula. And step 2, find y12 and y22 by short the circuit at port 1 when we determine v1 is equal to 0, and we will get this formula and this equation, and we will write to metric form this, and we will write to equivalent circuit from this. And this hybrid parameters, we will get this formula in this figure, and we will get equation in this figure is v1 equal h11 I1 plus h12 v2, and I2 is equal h21 I1 and h22 v2. And this hybrid parameter example, write the equivalent circuit in the form of H parameter. Step 1, find H11 and H21 by short the circuit at port 2 when we determine V2 is equal to 0, and we will write equation V1 is 0, V1 is equal R1 I1, and I2 is equal minus I1, and we will get this equation from this picture. And hybrid parameter example, step 2, find H12 and H22 by short the circuit at port 1 when we determine V1 is equal to 0, when we write the equation I2 is equal V2 divided by R2, and V2 is equal to V1, and we will write to equation, and we will write to metric form this picture, and we will write equivalent circuit from this picture. And a second hybrid parameters in another case caused by two-port circuit with V1 and I2 as independent variables called G parameter, and we will write to equation is I1 equal G11 V1 plus G2 I2. V2 is equal G21 V1 plus G22 I2, and we can write a metric from this, and we can find G from this metric. And next we will talk about transmission ABCD parameters. We will find equation from this figure, and we will find equation from this V1 is equal A V2 minus B I2. I1 is equal to C V2 minus D I2. And transmission ABCD parameter example, write the equivalent circuit in the form of G parameter. And step 1, find A and C by open the circuit at port 2 when we determine minus I2 is equal to 0. Then we get this equation, and we will get this equation from this picture. And step 2, find B and D by short the circuit at port 2. V2, when we determine V2 is equal to 0, and we will get this equation I1 equal minus I2, V1 is equal R1 I1, and we will get the equation from this picture, and we will write to metric form this. Okay, and this topic we will talk about filters, and the topic consists of topic 1, constant K filter, and 2, composite filter design. 1, low pass filter. For low pass filter, we will get this equation, and the cutoff frequency can be found from this equation, and the characteristic impedance of the T section and pi section are given by this equation. And next, high pass filter. For the high pass filter, we will get equation from this, and the cut-off frequency can be found from this equation, and the characteristic impedance of the T section and pi sections are given by this equation. And 3. Bandpass filter. For bandpass filter, C1 is series LC circuit from this equation. And the condition for bandpass filter is that both series and parallel LC circuit have equal resonant frequency from this equation. And the cut-off frequency for bandpass filter, the cut-off frequency we found from this equation. For band stop filter, C1 is a parallel RC circuit from this equation, and the condition for band stop filter is that both series and parallel LC circuit have equal resonant frequency from this equation. And the cut-off frequency for band stop filter, we will get this equation from the figure. And composite filter design by combining in case the constant K in derived shaft cutoff and the in derived matching section, one can realize a filter with the desired attenuation and matching properties. This type of design is called composite filter. And low pass constant KT section from this figure, and the high pass constant KT section from this picture, and constant KT section low pass with R0 is equal from this, and L from this, C from this, and omega C from this. And R0 from high pass constant KT section, R0 from this, and L from this, C is equal to this, and omega C. And in the live teaching section, low pass, we will get this equation from this, and high pass in the live T section, we will get equation from this, and low pass bisected pi matching section, we will get this figure, and high pass bisected pi matching section we will get from figure. And thank you.